This is my video on explaining how sulfur dichloride is formed. First, I will talk about how to make the Lewis structure. The first thing we do is determine the central atom. The central atom is usually the least electronegative atom and normally appears first in the formula. In this case, sulfur is first in the formula and it is also less electronegative than chlorine, meaning it is the central atom. Next, we count the total number of valence electrons for all of the atoms in the formula. Sulfur has 6 valence electrons, sulfur has 6 valence electrons, while 2 chlorine molecules have 14 valence electrons. This means that the total molecule has 20 electrons. Alright, next we can place the surrounding elements on both sides of our central molecule. We have 2 chlorine molecules, so we can place them on both sides of sulfur and create 2 single bonds. We can now complete the octets of the surrounding atoms using lone pairs of electrons and put any remaining electrons on the central atom. Also, if the central atom does not have an octet, we move lone pairs from surrounding atoms to form double and triple bonds until the central atom has a complete octet. In sulfur dichloride, we form 2 single bonds between the 2 chlorines and between the 2 chlorines and the sulfur to make it stable, and do not have to form any double or triple bonds. This is the complete Lewis structure for sulfur dichloride. Okay, I will now talk about how to determine the shape of a molecule. Since we now have the Lewis structure of sulfur dichloride, determining the shape is actually very simple. First, we look at our complete Lewis structure and identify the number of electron groups around the central atom. Electron groups can be single bonds, double bonds, triple bonds, and lone electron pairs. It is especially important to remember that double and triple bonds only account for 1 electron group, as this often causes people to slip up. In sulfur dichloride, we have 2 single bonds. In sulfur dichloride, we have 2 single bonds and 2 lone electron pair, meaning that we have a total of 4 electron groups and 2 lone electron pair. With this information, we can now look at our molecular geometry chart and see that sulfur dichloride has a bent shape and bond angles at 105 degrees. This is what the 3D model of sulfur dichloride looks like. Sulfur dichloride looks like on paper. The chlorine are in the plane of the paper, meaning that they are not behind or in front of the paper, and the lone pair of electrons is on top of the molecule. And we got this configuration from the back of our chart, right there. This is what the 3D model of sulfur dichloride, this is what the 3D model looks like in real life. Again, we have our chlorine's single bond to our sulfur atom with one lone electron pair on top and 1 lone electron pair to the side, and both of these electron pairs are at 105 degrees. The last thing I will talk about is the polarity of sulfur dichloride. First I'll talk about the difference between polar and nonpolar molecules. So nonpolar molecules have nonpolar bonds between 0 and 0.4 electronegativity difference, and they also have polar bonds whose dipoles cancel out. In addition, nonpolar molecules are also vertically and horizontally symmetrical. In contrast, polar molecules have polar bonds between 0.4 and 1.7 electronegativity difference and have dipoles that do not cancel out, meaning that polar molecules have a region of positive charge and a region of negative charge. Polar molecules are also symmetrical. So sulfur dichloride has polar bonds as 3.0 minus 2.5 equals 0.5, which is polar. Sulfur dichloride also has a dipole moment because the dipoles did not cancel out, as indicated by the net dipole. In addition, the bent shape of sulfur dichloride is not symmetrical. With this information, we can now conclude that sulfur dichloride is a polar molecule because it has polar bonds, is asymmetrical, and it has a dipole moment as its dipoles do not cancel out.